In today's class, my goal is to show you how we analyze data from factorial experiments when three factors were used. This example is based on one from this textbook by Box, Hunter and Hunter, called Statistics for Experimenters.
The experiments described in that example were run to find the combination of settings that would reduce the amount of pollution discharged from a water treatment facility. This is clearly a case where we would like to minimize the amount of pollutant. So minimizing our outcome variable would be the objective. Three factors were considered. The first one, factor C, was the chemical compound used. Let's call that compound P and compound Q. We don't really know their names. Factor T was the temperature of the treatment, whether we were treating the water at 72 or 100 Fahrenheit. And factor S was the stirring speed, either a slow speed of 200 revolutions per minute or a high speed of 400. Notice that every factor has two levels. And going back to that mathematical idea that 2 to the power k is the total number of experiments, k is equal to 3 in this example, so we get a total of 8 possible combinations. Here's a short quiz to test that knowledge. So let's take a look at the results. We will always present our data and analyze it using what we call standard order. Standard order requires that we create a column for each of our factors, so C, S, and T. Note that I could have used A, B, and C for the three factors, but very often we will switch to letters that actually match our factor names, but you don't have to. So back to the standard order table. And the rule is we vary the first factor the fastest, minus plus, minus plus, minus plus, minus plus. The second factor, temperature, is varied the next fastest between its low and high levels. So 2 minuses, 2 pluses, 2 minuses, 2 pluses. And then the last factor, S, is varied the slowest. So 4 low levels and 4 high levels. Those make up our entire table. Never run the experiments in the order of this table. The order must be randomly selected. So what we will do is add a column to our table to keep track of the order in which we actually ran the experiments. Also add a column over here for the outcome variable. In this case, the outcome was the pollutant amount measured in pounds. One thing that's so great about the standard order table is that we can get a quick sense of the factor's influence on the outcome variable. Take a look, for example, at how the pollution amount changes when we change the chemical compound factor C. That factor goes low, high, low, high, low, high, low, high. We see that same pattern in the pollution amounts. Take a look at the effect of factor S. The first 4 experiments have a very high level of pollution on average, while the last 4 experiments have a low level of pollution. That also matches with factor S. We can already tell just from this table that factor C and factor S are going to be really important to understanding the results. Let's go back to our cube plot. And this time our cube plot is actually a cube. We can draw it by showing the first factor along the horizontal axis, the next factor on the vertical axis, and the final factor S is shown in and out of the page in this diagonal way. Next, we transcribe the values onto this cube. This is really easy when we follow the standard order sequence. Take a look. 5, 30, 6, 33, then 4, 3, 5, and 4. I love this visual representation of the experimental data. It really helps us achieve our objective so quickly. Take a few seconds and answer this question. At what levels should we set our three factors in order to achieve the lowest pollution amount? That's right. It's very clear we need to use chemical Q, operate at low temperature, and with high stirring speeds of 400 revolutions per minute. Later on in the course, we're going to start examining what happens when you move outside this cube, and I want you to already start to think along those lines. But let's come back to the data we have right here and analyze the main effects and the interactions. start with the first factor C, the choice of either chemical P or chemical Q at the high level. If we look at the cube, we actually have 4 estimates of that main effect along each of the 4 horizontal edges. At high temperature and high stirring speed, in other words, high T and high S, that effect is equal to 4 minus 5. At high temperature and low speed, that's 33 minus 6. At T minus and high speed, in other words, S plus, it is 3 minus 4. And finally, at low temperature and low speed, it's 30 minus 5. So 4 estimates of the effect of the chemical. And the average of these 4 is equal to 50 divided by 4, equal to 12.5. Let's pause here. I always tell my students it's no good just calculating numbers. What does this value of 12.5 really mean in plain language? How would you describe this value to your manager who doesn't really understand any statistics? What it says is, on average, we expect an increase in the pollution amount when we go from using chemical P to using chemical Q. And remember, by convention, we report half of that amount. So report a value of 6.25. One further thing to notice is the discrepancy of that chemical effect at high S and low S. Notice the very large difference there. From the prior class, number 2C, this should be alerting to you that there's an interaction between factor C and factor S. But before we get to that, let's take a look at temperature. When we examined the table earlier, we didn't really notice anything special about temperature, and we should be able to confirm that numerically. We have 4 estimates of the temperature effect along the vertical axes: 4 minus 3 here, 33 minus 30 up here, 5 minus 4 back there, and 6 minus 5 here up at the front. So on average, we get a value of 1.5 as our difference. Or if we report half of it, that's an effect of 0.75. Lastly, let's take a look at the effect of stirring speed S. Along the 4 diagonal axes, we have 4 minus 33 up here, 3 minus 30 down here, 5 minus 6 here, and 4 minus 5 over there. The average of those differences is negative 14.5, and if we report half of it, that's minus 7.25. The minus 14.5 tells us that we expect, on average, a reduction of 14.5 pounds of pollution when we go from a low stirring speed to a high stirring speed. So clearly it's in our favor to use high stirring speeds in order to get that reduced pollution. You should always step back at this point and make sure these results make sense. Horizontally, we see going from chemical P to Q increases the pollution amount. That value of 6.25 looks about right. A small value of 0.75 for temperature also looks right, because it really has a very small effect. And finally, increasing the stirring speed has the largest reduction on pollution, a decrease of 7.25 units. You noticed while I was reviewing these results, I started to build up a numeric representation for you on the screen. We did that in class where we considered the ginger biscuits, and I just followed the same idea here. Y represents the prediction of the pollution. The 11.25 value here is the baseline. It is the average of all 8 of the outcome values: 5 plus 30 plus 6 plus 33 plus 4 plus 3 plus 5 plus 4 divided by 8. The other 3 terms are the separate effects of each factor. Those are the main effects. Let's see how we can use this model to make some predictions. Consider the situation where we're using chemical Q. In other words, Xc is coded as a value of +1. Let's use low temperature. So Xt is coded as -1. And also let's use low stirring speed. So Xs is -1. The predicted value is 11.25 plus 6.25 minus 0.75 plus 7.25. That's a value of 24. That's quite a bit different to the value of 30 pounds which was actually recorded. there's something we haven't accounted for, and that's the interaction between C and S. An interaction is when you have one variable behaving very differently depending on the level of another variable. We noticed earlier that the chemical effect has a change from 30 to 5 and 33 to 6 over here on the front face at low stirring speed. Yet, on the back face of the cube at high speeds, the effect is almost zero, 3 minus 4, 4 minus 5, very small amounts. It's very clear the stirring speed modifies the effect of the chemical. There's an interaction between S and C. How do we quantify this? Well, like we did in class 2C, we have to add a new term to our prediction model. And that term, the BCS, is multiplied by XC and XS. But how do we go calculate that BCS value? Let's go follow the same idea as we did in class 2C. We have two chances to calculate it. One instance at high temperature and one instance at low temperature. We will calculate both and then average the answer. And then, as we've always done, report half the value. So at high temperature, the difference due to C at high speed is 4 minus 5. The difference due to C at low speed is much greater, 33 minus 6. As you remember, interactions are always reported as half the difference going from high to low. In other words, that's minus 1, minus 27, which equals minus 28, and half of that is minus 14. Let's report that at the lower temperature. The difference due to C at high speed is 3 minus 4. The difference due to C at low speed is much greater, 30 minus 5. Report half the value from high to low, and that is minus 1 minus 25, which equals minus 26. Dividing that by 2 gives minus 13. So now we have two estimates of the interaction effect. One estimate is minus 14, the other estimate is minus 13. The average of those two numbers is minus 13.5, and when we report it, let's put in our model a value of half that amount. So in other words, minus 6.75. That's the value for BCS, minus 6.75. Now, let me just pause here for a second and emphasize that this is all very tedious if you do it by hand. And we're going to show some computerized ways to do this faster in the next few classes. But I always recommend let's start with by hand and then see the advantage of it later on when we go to computers. So let's take our predictions now again from the previous example and see if they are improved. The predicted value earlier was 11.25 plus 6.25 minus 0.75 plus 7.25. But now with this interaction term, we have an additional part, minus 6.75 times 1 times minus 1. What that means is we actually get an additional amount of 6.75 due to the interaction, getting us a prediction of 30.75, much closer to the actual value. Notice here that the interaction actually works against us. That interaction has increased the amount of pollution. We could also calculate CT interactions and TS interactions. I've only shown you for CS interactions. In fact, there's even a three-factor interaction, a CTS interaction. But all of this gets very tedious and error-prone. Coming up in the next module, we can't wait to show you some computerized shortcuts that will take care of all of this work for you. Now, at the risk of this class going on a little bit too long, I want you to sit back and just think about that interaction for a second. Don't just see it as a number, but let's try to interpret what's really going on over here. Why does chemical Q appear to be less effective at low speed, but at high speed it works really well? Maybe chemical Q just takes a little bit longer to dissolve in water than chemical P does. At low stirring speeds, chemical Q is not effective, but at high speeds, both chemicals are equally effective. Now here's where experiments can be really powerful. We saw that the lowest pollution was over here in this corner when we used chemical Q with high speed and low temperature. But what if the government requirement was pollution had to be smaller than 10? And imagine also that chemical Q cost you double the amount of chemical P. You can see where this is going. We can see that any operating point on this plane would be effective, as long as it's not the point with low speed and chemical Q. In fact, it might be a whole lot more economically profitable to operate at this point over here, producing 5 pounds of pollution. We still meet the requirements for safe operation because we're below the government level of 10 units, and we use less energy for stirring and a cheaper chemical, P. Actually, what we've done here is considered an additional outcome in our mind, profit. Recognize that profits or cost often play a role in any system, so you should always be aware of the economic impact of every corner in your cube.
To end this class and this example, I want you to consider this. Does the fact that temperature having a small effect imply that temperature is meaningless? The answer is no. It is important to recognize that even effects with small numbers have an important interpretation. It means that over the range of temperature selected, in this case between 72 and 100 Fahrenheit, that temperature has a small to negligible change on the pollution amount. Now this is a key insight because the engineer or operator can take this and select operating conditions which are the most economically advantageous. Again, this comes down to profit. It is conceivable that when using lower temperature, we will save energy. And because temperature has such a small effect on the system overall, it means that we will not significantly affect the pollution level when we operate at low temperature. That's a great result. So I want to thank you for staying with me during these examples. I know that they've been longer than normal, but I hope they have been insightful. In the module coming up next, we're going to start looking at how we can do fewer experiments, but still get a good amount of information about our process. Hope to see you over there.